Welcome to Are You Chemistry GCSE Ready? This playlist takes you through loads of example questions and guided solutions for every single topic in your chemistry GCSE. So it's a perfect way for you to test your chemistry knowledge. If you feel like you need a quick review or you just want the ideal revision companion for these videos, then make sure to download my free chemistry GCSE revision notes. I've linked them in the description below. Or if you're ready, let's dive straight in. Exothermic versus endothermic. So what's the difference and how can we tell which one a reaction is? So exothermic, remember exit, releases heat energy, and endothermic, entrance, takes in heat energy, which is why your exothermic reactions, substances get hotter as they release this heat, and your opposite for endothermic, the substance gets colder. Make sure you're clear on the way round those two things are, both which one releases heat energy and which one takes it in, and what happens to the temperature of your substance. In terms of your enthalpy change, they're negative for exothermic reactions and they are positive for endothermic reactions. How can we tell which reaction is most exothermic? That's going to be the one that gives us the largest temperature rise per mole. So we know the substance gets hotter in an exothermic reaction as this reaction releases heat, and the largest temperature rise per mole tells us which one is the most exothermic. It's important to bear that per mole in mind when you're thinking about this, because it could just be that you have a very large amount of a not very exothermic reaction would give you also a large temperature rise. So just be aware of that. Reaction profile. So draw a reaction profile for an exothermic reaction, and what does it show us? So remember, your profile has potential energy on your y-axis and then progress of reaction along your x-axis. And the higher something is up your potential energy axis, the more energy it can release. Okay, a little bit like this was the analogy in the notes. It's like a battery's charge. Reactants and products. Remember, for your exothermic reactions, your reactants have more potential energy and your products have less potential energy. And since along your x-axis you're going with progress of the reaction, closer to the origin should be your reactants, and then further away from the origin should be your products. And remember, you have this kind of shape here, and that little hump shows you the amount of energy that you need to overcome first to have this reaction take place. And remember from the work we did on your reaction rates, that's called your activation energy. So that amount of energy there, the amount that you have to climb in order to go down this hill, is your activation energy. And there, from your reactants to your products, that's your enthalpy change, and you are going from something higher to something lower, and that's why you get this enthalpy change as negative for your exothermic reaction. And it's important you get that arrow the correct way round from reactants to products, which means that this is pointing downwards. Remember, for your endothermic reaction, you have the opposite way round. Your reactants are lower potential energy than your products, and you have this kind of opposite curve for those, and your enthalpy arrow would therefore be going up for that one as well. Bond energy calculations. Calculate the enthalpy change for the following reaction. So you've got your reactants and you've got your products. So you've got the bonds being broken on your reactant side and the bonds being formed on your product side. And you just need to work out the amount of energy for both of those first. So on my left-hand side here, and remember this tip of crossing the bonds off as you go, I've got one nitrogen single bonded to another nitrogen. I look at my table and that's 163 kilojoules per mole. And then I've got 1, 2, 3, 4 of these nitrogen single bonded to a hydrogen, 391
is the bond energy from the table. So 4 times 391 gives me 1564. And then finally, on my reactant side, I've got my oxygen, double bonded oxygen, and from my bond energy table, that's 498. So in total, 163 plus 1564 plus 498, 2225. Bonds being formed then, I have got 941 coming from that triple nitrogen bond there. And then I have got 2 times, okay, so 2 times all of what I'm about to say, the following, which is 2 of these OH bonds. So each of these OH bonds is 463 from my table. So 4 times that number, 4 times 463 is 1852. So don't forget with these bond energy calculations, you could work out the energy first for that HOH by doing 2 bonds, so 2 times that 463, and then you need to remember to multiply that whole thing by that coefficient in the front, so by 2, which is where we got the 4 from here. 2 times 2 is 4. Then I add those together, 491 plus 1852, 2793. Then I do my 2225 minus my 2793, and that gives me a negative number here, and that means that this is an exothermic reaction. I've decided it's exothermic because that answer is negative, that final answer. Okay, an enthalpy change calculation. So reaction containing 3.1 grams of fuel led to 40 grams of water rising by a total of 5 degrees Celsius. Calculate the heat energy for that reaction and the overall enthalpy change in kilojoules per mole. Give your answer to 2SF, and then we're given the information. Water has a specific heat capacity of 4.2. The fuel has an RFM of 231. So first things first, I needed to calculate the heat energy for this reaction. So Q is MC delta T. How much energy was released in this reaction? Well, we had, and remember that's the mass of the thing that's changing temperature. So here, that's the mass of the water, not the fuel, because the water is the thing that changed temperature. 40 times specific heat capacity, which is given to us as 4.2, times change in temperature, and it gave us that by saying it was a total rise of 5 degrees. It might have given us a final and an initial temperature, and we'd have to find that change in temperature ourselves. 840 joules. Enthalpy change then is that heat in kilojoules divided by number of moles. And so firstly, I need that Q in kilojoules, so 840 divided by 1,000 to convert from joules into kilojoules, 0.840 kilojoules. And then 3.1 grams of fuel into moles. I need to remember my work going between mass and moles and know that it's my mass divided by my relative formula mass, given for us as 231, gives me my number of moles, 0.013, etc. Change in enthalpy, 0.840 divided by 0.013, 62.6 kilojoules per mole. But I was asked for it for 2 significant figures, so 63 kilojoules per mole. Make sure you check out for those in your exams, the 2 significant figures, because it's an easy mark to gain.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free, so why not?
Okay, first tip is don't get your enthalpy changes mixed up. So a rise in temperature means a negative enthalpy change and is exothermic, whereas a decrease in temperature means a positive enthalpy change and is endothermic. So make sure those are straight in your head. If you do the bond calculations for your spec, make sure you cross off the bonds as you count them during the bond energy calculations. It's easy to double count or miss them out, and it will stop you making silly mistakes and losing unnecessary marks.